Let's see a some more elements about the density matrix and some pitfalls that we might come across in doing simulation. You can also write the density matrix as a function of angular momentum operators. So if you calculate it, you can notice that this matrix representing alpha is the sum of the identity matrix and Iz. And more generally, if you write the density matrix as a function of the polarization of the spin along Z, here is the form that you get. And the polarization is defined here. That depends on the field, the temperature, and the gyromagnetic ratio of the spin. A common simplification that you will see in textbooks is that rho is Iz, or if not, we do all the calculations on Iz. And there's a danger if we do that, is that if you want to use the formula that I've shown earlier to calculate the expectation value, you end up with a division by 0 because the trace of Iz is 0. So we have a problem, and it's nice to simplify the problem to Iz. So let's understand why and why people just write Iz. If you decompose the expectation value of Iz for density matrix that is polarized with polarization P, and now if we go through the details, we can separate the trace of a sum is the sum of the traces, and so you get this expression. And if you calculate the individual terms, what you get is, as expected, a half, and it's multiplied by the polarization. And so it becomes sort of clear why people drop the Iz, because the trace of the identity matrix doesn't contribute to anything, because when you multiply the density matrix with Iz, it gives Iz, and when you take the trace of Iz, it gives 0. So it's never contributing to the expectation value. That's why we don't want to bother writing it all the time. But we have to keep in mind that it's important for the normalization, because it is 0, so we need the identity matrix to have an appropriate trace of 1 or some real number for the density matrix. So now we're going to move on to describe the spin system for 2 spins, and for this we need to define the outer product or Kronecker product. Here I've written in full how this operation works, and we will see how to use it in practice. So for example, if I have 2 spins and 2 wave functions, psi1 and psi2, the states of these 2 spins together is described by the outer product of the 2 spins. And if you write it in full, you have on the right the expression. You have started with 2 coefficients for each spin, and you have 4 coefficients in the end. This works as well for the density matrix. You can in fact prove, if you take the expressions of the density matrix as the product of the ket and the bra and do the outer product, you can show that this formula is right. And if I expand it for 2 spins being in alpha, that's the formula on the top, I get this simple density matrix with just a 1 at the top, which means that I have only one state that is populated, and it's both spins being in alpha. And more generally, if I want to represent the density matrix for 2 spins in polarization P1 and P2, here I've used the expression that I've shown on the previous slide, which is the density matrix for the particle 1 with polarization 1, and then on the right of the outer product cross the density matrix for the spin 2 with polarization 2. And if I do the simple math for this, I get now no longer a half of the identity matrix, but a quarter, and I get this formula with Iz multiplied by P1, I1Z, and I2Z multiplied by P2. And we have this term that we often don't care about in normal NMR at low polarization, which is the product of Iz, I1Z, and I2Z with the square of the polarization, because P1 times P2 is very low in conventional NMR. But here I haven't explained to you what is I1Z and what I2Z. I've explained earlier IZ, so I need to go in some more details. I1Z is the outer product of IZ with the unity operator, and I2Z is the outer product of the unity operator and IZ. What does it mean? It means that I1Z is operator IZ operating only on spin 1. So an operator that doesn't do anything on spin 1 is precisely the unity operator. So you have the unity where you don't want to act on the spin, and you have IZ where you want to act. If you write it in full, this is what you get for I1Z and for I2Z. Of course, we don't want to bother doing this calculation by hand all the time. It's just convenient to do it once or twice to have a clearer ID. So if I apply I to Z on my density matrix, it will give me the expectation value of spin 2 along Z. If I want the expectation value of IZ for both spins, I take the sum of I1Z and I2Z, and from now on, the term IZ will not refer to this one, but in the context of two spins, IZ refers to the sum of the two. So we have to be careful. There's a obviously this is slightly wrong, because in fact we this is not completely written, but we just assume that the reader understands that here this is written in a space of a subspace of a single spin, and this is in the full space of the two spins. So let's go to MATLAB and write these Hamiltonians that we will use from now on. If I want to write I1, now I will call them I and S because I find it more convenient. So IZ, IZ will become the Kronecker product, and for this we simply write Kron. This will be IZ. No, let's define it differently like this, otherwise I will have problems. And so you might remember that this I, if I write it here, is the identity matrix. So this will be for spin 1, and for spin 2 it will be the opposites. So if I run this and I uncomment it, you see this is what we saw in the on the PowerPoint with the minus signs of plus plus minus minus plus minus plus minus. We will need later on the same thing for IX. I will simply copy all this. Oops. So now I have defined the angular momentum operator for my two spins in three directions in the space describing the two spins together. And I also want to define the total angular momentum operator, which is I1x plus I2x. Same thing for IY and for IZ. I run the code, so they are now defined in my workspace. So now we have operators, but we also need the density operator. So rho 0 will now be, we can define it like this, the Kronecker product of, how do we want to write it? We can, for example, write it like this, the identity matrix divided by 2 plus IZ. So this is spin 1 polarized along the field. And if we assume that spin 2 is as well polarized along the field. We write the same here. So if I run the code, and I made a mistake. Oh, so yes. So here I have a problem. Is that I have defined IZ. When I run the code again, I have overwritten I1x and these functions. Yeah. So if I run this code again, now it should work. So the way I'm trying to write it is not valid. So I can either write it like this. This will respect what I've shown earlier, and we will see some functions that I've created to just go faster with this. Okay, let's go back here. I also show you here that there are some other operators, two-spin order operators. But for today, we are not going to use it. It's just that I write it here to show you that what we have seen for the simple single-spin operators also expands to more complex terms, but this will be for next week for two-dimensional experiments. With this, we can write the Hamiltonian for our two spins. You see the first term, omega 1 I1z, is the Zeeman precession for spin 1. Omega 2 I2z is the Zeeman precession for spin 2. And this 2 pi j I1 dot I2 is the term of the J coupling. So I assume that we are in an isotopic liquid, not doing solid state for now. And I written in this form is what we have seen in the beginning of the presentation, is the vector containing the order angular momentum. If I write it in full, taking dot product, this is what I get. This is the very general form, but in many cases, especially in heteronuclear system, when the difference in Larmor frequency of the spins is... Oh, I wrote... This is wrong, sorry. This is the opposite, is when the difference in Larmor frequency is great with respect to 2 pi j, then we can just drop the parts I1y, I2y, and I1x, I2x, and get this easier Hamiltonian, which is always true for heteronuclear system at high field. Now we can do the same work we have done earlier, but for our two spins. So I'm simply going to copy the whole code and modify only what I need to modify. So let's assume that we are at 400 megahertz, and we define two frequencies. Now I will call it omega I and omega S, or to be consistent, let's call it I12 and I11, 0. You get it. And now let's say that the Larmor frequency of the second spin is divided by 4. So this would correspond to a proton and a carbon at high field. We need to modify the Hamiltonian. So this is the Zeeman term for spin 1, the proton, the Zeeman term for spin 2. I'm going to separate it so that they are clearer. I2Z. And now the J coupling Hamiltonian, so I need to define J, let's say 20 Hertz. And here I need to add, to write in all the terms. I'm going to write it in full, the full J coupling Hamiltonian, although, as I told you, we don't need to consider all the terms at high field and heteronuclear system, but it will be useful when we move to homonuclear system. We can keep these parameters for the pulse. But now we have to think about the pulse Hamiltonian. What spin do we want to pulse on? So if I write Iy is the angular momentum operator for both spins at the same time. So if I say that I'm pulsing only on the proton, for example, I have to write I1y. So now it's this Hamiltonian is only affecting the proton. I remove this for now. Let's check that this is right. So rho 0 was defined here. This has not changed regardless of, so H1 is defined here, so it doesn't change the definition of U1. So at this point I have rho 1, which is a density matrix describing spin, the carbon spin along the magnetic field, and the proton spins along the along X. This time I'm gonna just modify slightly the parameters. And the width, I need something larger this time. Yeah, and I can keep this. Again, here we need to think about what we want to display here. If I write this remains true because it depends of H0 that I have rewritten here. But if I write this, it means that my receiver is recording both the proton and the carbon at the same time, which is wrong. So by replacing Ix by I1x, it means that I'm looking at only the proton. And now let's run the code. It's slightly longer because we have much higher dimensions now. And if it is so long, it suggests that there's a mistake somewhere. Okay, let's have a look. So to stop the code, I go in the command window and I do Control C. Let's split until here, for example, and run only this part of the code. So let's have a look at H0. So it has the appropriate size at least. That's one thing. It's a 4x4 matrix as we expected. What is the value of n? N is immense, so maybe this is why it takes so long. Let's make it narrower. So 500 Hertz, for example. And now, okay, this is slightly less. Let's see if we can run it now. This is quite long. Okay, it worked. So where is our peak? It's at 1 ppm. So this makes sense. Why 1 ppm? It's because here I had chosen 1 ppm. So we have a peak, a proton peak at 1 ppm, and because of the way I've defined the pulse, it's negative. We can simply ask the function here to change the phase like this. And now, so I write phi, this is the option for phase, and I give the value pi, and this will, oh, no, there's a mistake. So there must be some other mistakes, and there's a good reason for this. Let's see, can someone tell me why this density matrix is not appropriate? First, we should see a doublet, and we see a singlet. Why do you expect to see a singlet when we have two spins coupled together? Can someone tell me this? No, they are not, because they have a factor 4 in frequency. The thing is, I have chosen a density matrix where both spins are fully polarized. And this is not you don't find it in reality. So it means that your proton spin that sees a carbon spin that should split it in two only sees a carbon spin polarized along alpha, and then you only have one of the peak of the doublet. So to make it easier, I have created this operator, thermal equilibrium density matrix, with some options. So I have to write here that I have a proton spin and a carbon spin represented by the number 1 and 13, to say the field, for example 9.8 Tesla, and the temperature. And this computes the thermal equilibrium density matrix for the two spins. And in this case, where the polarization of both spins is near zero, you indeed see a doublet. So let's run the code again. Oh, I had not seen here. The parameter phi is not known. So the reason why you had the wrongly phased signal earlier was just that the name of the parameter was this one. If I run it again, now obviously I've erased. I've run the code until here, so I'm making the Fourier transform of zeros. So let's run it in full again. It will take a little bit of time, as you've seen earlier. So I'm going to repeat the problem here of why we had a singlet. The reason why we had a singlet is that the J coupling will split the peak in two, because some proton spins see a carbon in alpha and some see a carbon in beta, and this causes the splitting. Here I had defined my initial density matrix with everything along Z, so they are only carbon in beta. This doesn't happen in conventional NMR, and that's why we see doublets. So I had to recalculate to redefine a density matrix that is more appropriate. Now you're going to say that I'm... Oh yeah. Yeah. Oh yes, yeah, you are completely right. Maybe if you want, I can run again. Let's make it a bit shorter. 3 seconds, and like this will be faster. Let's use the density matrix we had earlier. So let's assume that the temperature is 0, and it's fully polarized, which is the same as being fully polarized. Okay, I run it again, and here I still have a problem here. Oh, it's pH the way I defined it. You see, I don't even remember my own code. Okay, so the calculation is done. The phase is right now. And if I zoom, you are right, completely correct. The peak is not centered at 1. It's centered, it's on the side. And here would be the second peak of the doublet. So I think it answers your question. Now let us put normal temperature. I run the code again. It's running. Now it's propagating. And we have our doublet. Oh, sorry. As expected, it's centered at 1. It's also interesting to do a slight modification in the pulse. Now you can start to play very easily if you want to know how the proton spectrum looks like when you pulse on the carbon as well. If you remove this one, it now means that the Hamiltonian of the pulsing, H1, is no longer just acting on the proton, but on the carbon as well. So it's like if I were pulsing on both channels at the same time. But because here it's in the detection part, I have I1X, I'm only detecting the proton. Let's run it again. So we have the same result. In fact, this was more interesting if we have zero polarization. So now we have again the carbon that is fully polarized, but we see that when we pulse on the carbon, remember, now we have an initial density matrix where the carbon is polarized, but we see a doublet. Why? Because we have pulsed on the carbon, and this has equilibrated the population in the carbon. Just now it's easy to play with this with these parameters. You're just changing the operators during the pulse and all this. And last thing I want to show today, moving from here, I'm just gonna make it like this in the final version. Last thing I want to show today is for a homonuclear case. So I'm going to copy the whole code. This was heteronuclear. Copy this all. And we're going to move to homonuclear. Homonuclear. Doesn't change the definition of the Pauli matrices. Now I don't have two carbon, let's say I have 2 protons. So the Larmor frequency, the carrier, let's say it's still 400 megahertz. I will define D1 and D2 for the 2 spins. For example, minus 0.5 ppm. Now with these chemical shifts, I can define my 2 Larmor frequencies. Let's keep the same here. And with the homonuclear case, that's where it will be interesting to see what happens whether we write the Hamiltonian, the J-coupling Hamiltonian in full or not. Now we just have to think about the pulse Hamiltonian. So of course, if I leave the pulse Hamiltonian like this means that I'm only pulsing on spin 1, which will correspond in a homonuclear case to a selective pulse. I don't want a selective pulse. This remains the same. These are FID parameters, I don't need to change them. And again here, so when I calculate the propagator and the the sandwich formula, this doesn't change because this depends on H0, not changed. But here, for the detection, I want to detect, I assume that my channel is detecting both spins. I run the code. I propagate. I'm going to get rid of the FID here. So here is what we get. So, do you know what is this? I guess you do. Can someone tell me what we are saying? Come on, guys. Okay, no. Yeah, but what I expected someone to say is that we see the roof effect. Like the difference in intensity of the 2 peaks. That's what I wanted to show you. Maybe I don't like to see it cut like this, so a feature that I've implemented here is zero filling. Oh, the options is named 0, and the value I can, for example, say 6 times n. So n is the number of points of the FID. So here I multiply the size of the FID by 16 to make the spectrum slightly nicer. So we see our Lorentzians better. Okay. So this is the case of strong coupling. So, and in strong coupling, when the difference in Larmor frequency becomes comparable with the J coupling, we have this so-called roof effect. And now if I compare the same thing but neglecting Ix and Iy, which means that I write the simplified J coupling Hamiltonian without the Ix and Iz term, Iy term. I run it again, propagate, and plot. And now I have recovered my two Lorentzians with a symmetric pattern. So this is really the effect of you might try to Hamiltonian like this. It might be fine depending on the situation, but here in this case, we are obviously oversimplifying the system because this is not supposed to be symmetric. It's nice also if I go back to the non-neglected case. So I had a J coupling of 20 Hertz. Now just to play a little bit, let's see what happens if I make these two peaks where I don't neglect the full J Hamiltonian. If I make them very close, I run the code. So here I have a very strong roof effect, and it starts to look like this looks like a quadruplet. Let's play a little bit more with the numbers, which will be clearer. Yeah, so here we properly see the doublet 1 and the doublet 2, but they have this very strong effect of the roof effect. And if I make them equivalent, we have a singlet. I put them back as earlier for the final code. So that's all I wanted to show you today.